Okay, we're back for the next in this series of videos, and this might be the last one where I actually demonstrate features instead of talking about the internals. I want to switch gears to talking about compiler internals and kind of how the thing works in the future. But there's a few things I really wanted to cover before I do that, and one was a little bit of follow-up on schema and what goes on with schema stuff and some of the choices that we made and kind of why we made them. And I also want to talk about the JSON output because that's super important. So that's what I'm going to do today. Hopefully we can do that in not too much time. So I started with this pretty simple sample. I have this table T, and I have this procedure that selects the stuff from T, and I have this other procedure that inserts into T, and I have this thing that prints the contents of T. And let me just go over these fairly quickly. First, let me touch on this thing. This is actually new. We had one similar to this, but you may recall that when you do a select statement, you get a result set, and you get all these helper functions for fetching the result set and accessing the result set and so forth. If you intend to use the procedure only from within CQL and you don't want it to have the C interface and you don't want the extra overhead of creating the result set, you can provide that as of a few days ago. We used to have something that did part of it. You could do this to just not have the getters, but just have the fetcher. This basically suppresses it all. And the reason that I put this here today is, well, okay, I get to mention that we added this, but also because it makes the C code easier to read because we won't have all the boilerplate for all those getters and stuff. And so as we're walking through what each of these mean, we can look at the underlying statement and we don't have to read the getters all the time. So in the interest of the demo, that's helpful. Okay, so we have just a very simple table, some nullable columns, some not nullable columns, a primary key, and we're going to do a little bit of schema versioning and kind of see how this plays out. Notice that T wasn't created any particular schema version, so it's part of the quote baseline, but that's okay. Baseline tables can be versioned after the fact. If you like, baseline tables are implicitly created in version 0. Okay, so we have a thing that inserts. Notice we're using the cool syntax like T, so we're going to get arguments that match T. And here we're going to insert into T from the arguments. So I really like these forms, not just because they're less typing, but they're very robust. You don't have to worry about getting the args in the right order. You don't, like, anyone can look at that and see exactly what's going to happen. If T had 75 columns, you might have to be like, oh God, okay, wait, this one, does that one match with this one? And does that one match with that one? And actually, we're going to be doing something about that too in the future. So you can look for that. I'll probably start blogging about those things. And here's a little thing that prints. Okay, notice we get the cursor by doing the call. Okay, clearly we could have just done, select star from T here, which would have been the same. But you could imagine if it was more complicated, or if that particular selection was, needed filtering or whatever else, you can use the procedure. So here we're capturing a cursor as the result of that select. And then we're going to loop over that cursor and we're going to call printf on each row. And we're using this new little helper, Cql Cursor Format. Cql Cursor Format expands into code that formats a string for the shape of C regardless of what the columns are. And that's really handy because there's lots of funky cases like, you'd think, okay, well, what's so hard about that? I could just, do like some, c.x or c.y, well, in this case, I guess c.id or c.t1 or c.t2, I could do something like that. Well, first, that's awkward if C has 75 columns. Second, you don't get column labels, and column labels can be really handy when you're looking at the diagnostics. But more importantly, some of those columns are nullable. And the moment you throw even one null in a concatenation, the entire result is null, and you just don't want that to happen. So as you'll see in the rewrite for this, because this just turns into a case win, it pulls out whether or not the column's null and turns it into null and puts in a label. And we'll look at that in just a second. So let's look at this program just like the way that it is right now. We're just going to do the usual build. I'm not actually going to compile anything to runnable code today because we don't really need to, for purposes of this exercise. Okay, so I have this in a impressive file name X, which I always use for Scratch. Okay, so here's our original selection. Select star from T. Now, look at the code. Okay, notice it does not say select star from T. It says select ID T1, T2, T3, T4 from T. And today we're going to get into why that is, and it'll be easier to illustrate. But for now, note that it's expanded, okay? And it's just expanded, and all it does is prepare that statement, and it's going to go into result, which is the out arg right here, okay? And so when we call this thing, we get a statement back. Normally the fetcher calls this and you call the fetcher. But today I suppressed the fetcher, so it's only going to be usable from other bits of CQL. Okay, here's the insert. Again, look at the statement. All the columns were expanded and all the values are expanded. And if you look at the signature of the function, you'll see it's got T1 text, T2, T3, T4 with an underscore. Okay, and that's our sort of internal convention to avoid these kinds of problems. So it's clear looking when you are referring to the column versus when you're referring to the value. Now, actually, this could have been ID because it's unambiguous. It's always unambiguous, really. It can be ambiguous when you're doing like inside of a select or something like that, where you can use the variable, the column name loose, and you might want to bind the one with the other. So sort of by convention, we put underscore after the names of arguments, and the from arguments or the like arguments end up having this underscore as a consequence. So so great. Okay, so this is fabulous, and you just get a simple insert, nice and easy. And here's that statement. Okay, again, prepare and bind, and it's just bind. Okay, really simple. Here's one that's not null. Okay, so it's slightly different binding. And then the fetcher, okay, you can see what it expanded into. You get this ID T1, T2, T3, T4. Okay, this is just a straight printf. So that was that whole function call was rewritten. So it's just syntactic sugar. And so there's the string, and then we do this. Each one of these does case when ID is null, then null, else printf %d c.id. Okay, so each of the pieces is being turned into a string. So they'll all be string, and then each of the arguments is going to be either null or the formatted version of the thing. So like if we look here, here's the formatted version, and they're all the same. If T1 is null, then null. If this is null, then null. If this is null, then null. In fact, for T3, we could have simplified this because T3 can't possibly be null. So fair enough. This is going to compile to nothing anyway. And C4, likewise. Okay, so you can see what the pattern is going to be. Each one of these turns into a simple case statement to format the thing as a string. If it had been floating point, you know, there'd be %f there. You get the idea. Okay, so it's a two-stage printf. So none of these are going to be null at all. There's never going to be any nulls here, and instead you'll get the string literal null. Okay, great. So there we go. This is the code for it, and you can see it actually gets fairly complicated because it's got the when, and then another when, and then another when, and then another when, and then here's the printf. We have to convert all the strings into C strings. So we make these temporary C strings, and then we do the formatting, and away we go. Okay, because we need to call SQLite3 mprintf to do the printf, and it doesn't take string objects. It takes C strings that are null terminated. So we do that little conversion, and then we free this all, and that's it. So that's great. It's super handy for diagnostics. I absolutely do not recommend this for production code. It's just not suitable for anything. This form here, or if you like, this construct. This is great for debugging code or for test logic for reporting, like, you know, what went wrong. You know, you can use it to dump contents of a table if you have a test that's failing or something like that, and you might want to see what your cursors look like, and so you can help diagnose what's going on. So it's very useful in debug logic, not for use in production. But a lot of features we added really are all about debug logic. We've also recently added this one, so you can do diff val C1, C2, and it'll tell you what's different about the two cursors. Again, super useful in a test because one of these could be like the expected values, and one of these could be like the actual values. And then you could just quickly get what's the difference, and you can write very simple expectations without having to, add new expectations every time new columns come along and so forth. Okay, so super simple. And let's just go back to the baseline. Okay, so why am I even doing this? I'm going to do a little something here. We're going to say delete in version 1. Okay, great. So now when that table, when T2 goes away, it's been logically deleted. It can't actually be removed from the schema. So if we did a select star from that table and let SQLite expand the star, then it would still include the column that's supposed to be gone. And so that would be weird, and it would break all kinds of stuff, because none of the code is expecting that column to be there. So, and if you did that, then select star would basically be useless, right? In fact, most of the time, people recommend that you not use select star in production code. And actually, select star is comparatively safe to use in production code in the CQL environment, precisely because we expand it, because we know exactly what it means at the time you compiled. So in this case, it's going to be exactly the same as ID T1, T3, T4. So let's just go ahead and rebuild that. Okay, if we look at x.c now, there's our select statement. T2's gone. Okay, so it's quite safe to use that star. And furthermore, when we look at the insert statement, okay, T2 is again gone. Okay, now this works because T2 is a nullable column. It's not really gone in the schema. There's no way to get rid of it while preserving the rest of the table contents. So it's logically removed. Okay, so what that means is we can't let you do this. Okay, I'm going to do this. Delete that in version 2. Yeah, no. Okay, it has to either have a default value or it has to be nullable, because it's going to be missing in all of the inserts. You can't mention that column anymore. Okay, so, and lots of stuff, goes, cascade goes wrong because the definition of T failed. So most of those errors are kind of specious. So this right here, you can't get rid of a not null column in the future. It either has to be nullable or it has to have a default value. It won't let you delete a not nullable column because there's no way to logically remove it. It's going to have to appear. You're going to have to mention it in all your inserts. So logically deleting it is problematic. So if we took it away or something, I mean, we could do some goofy thing like every time you mention a column that's been logically deleted, put the value 0, but that's really problematic because 0 might have some semantic meaning. Maybe the quote nil value is -1, or maybe it's quote, or maybe it's, I don't know what it is. So we just don't go there. We will let you logically delete anything that has a default value because it can be not mentioned, and we'll let you logically delete things that are not nullable. Likewise, when you insert columns, we have the same problem in reverse. If you try to insert this, that'll work. Okay, there's a nullable text column. Let's build that. Okay. And notice I didn't do the previous schema validation and stuff here. Normally you would want that as well. But there it is, T5, it's fine. Everything's good to go, right? And on the insert side, the same. Okay, again, so you can use these very simple patterns that let you do, column-wise. And if you look at the dumping code, it's also like, there it is, okay? T2 is gone, T5 is there. So, it's all very much dealing with the logical columns. Okay, but if you try to do this, again, you're going to get errors. You should have got an error. Oh, I forgot to put the not null. Not null. That was the whole point of that. There you go. Same problem. Okay, it's the same problem in reverse. If you add a not null column, you're going to break the world. Because you basically have to visit every stinking insert statement everywhere and figure out what that is, and all the code everywhere has to decide kind of what's the semantic meaning of a not nullable column. So to say nothing of like, what would the value be? Like how is SQLite going to fill that table with new not nullable values, Whereas if it has a default, then again, it's clear what needs to happen. So So nullables or with the default value. Great. Okay, and that's really all I wanted to say about this. And because of these very simple rules, this is actually quite safe to use, and that's important. And these patterns, again, they're quite safe to use because you're going to get the code as it was as it was when it compiled. Now, what's also interesting is because those columns are effectively hard-coded, in the event that the schema changes out from under you, with the code not recompiling, it's still okay because this procedure is going to produce what it always produced. It's not going to just pull whatever columns are there. It's going to pull the 4 or 5 columns or whatever it was that existed at the time this procedure was compiled. So whatever the declared schema was. So even if you add new columns after the fact, without going through CQL, without recompiling, like by doing live alter statements, it's still pretty good, right? Because these are exactly what they were, and they're going to be consistent with the schema. And whatever that procedure did, it's going to continue to work. It's going to continue to do whatever it did. If you change the schema and inform CQL, it'll be, extended again as usual, and that'll be great. So yeah, so this is really very much the same as listing the columns, but you don't have to, and the columns will be computed for you at compile time rather than at runtime. So, and that's what's really important, and that's kind of the dangerous part about using star. Likewise here, we're going to attempt to insert with what you've got. So if someone changed the schema out from under you, if they did it in a sensible way, adding only nullable columns, then this will continue to work like always, and everything will be just fine. If they add a new non-nullable column, then this will fail, because the columns will be missing, and you'll get runtime errors, and you should be able to run that down, fairly quickly. So in no case are you going to get any sort of wonky situations where you were expecting 4 columns, but you got 5 columns, and the columns are now in the wrong order, and you bind to something, and you're going to get other than what you expected. You're always going to get exactly what the code expected. Okay, so now let's switch gears, because this is a good time to talk about the JSON schema. So I'm going to continue to use the same example because it has lots of good things. And so we're going to do cg-x.j rt JSON schema. Okay, and what did we do? Oh, I still had errors in X. Okay, got to get rid of this one. Great. And I'm missing the comma. Too many commas. Okay, that's how you know it's not. That's how you know this is not scripted. Okay, so I guess I could have called this x.json. Okay, here I'm gonna just call it x.json because. Okay, yeah. All right. So here's the JSON output. Okay, and the JSON output actually has really some pretty cool information about what's in your schema. Okay, and it tells you lots about your program and whatnot. So there's multiple sections. The first one is tables, and so here table T, it's not a temp table. It wasn't created with if not exists. It doesn't have without row ID. It wasn't created in a particular version. Okay, columns, name, ID, integer, is not null, is added, is primary key. Okay, so really it's telling you pretty much everything you need to know about that column. Here's T1, T2. Okay, notice this one is marked is deleted, and it was deleted in version 1. Okay, here's T3, is not null was 1, T4, then T5 was added in version 2, and that's all we have right now. The primary key is ID. There are no foreign keys or unique keys. That's it. There's currently no views, triggers. And then we come to the sections that have to do with stored procedures. So in the JSON world, there's 2 kinds of stored procedures. There's the, quote, simple stored procedures. I'm making air quotes right now. And those are stored procedures with a single SQL statement, okay? So there's no control flow. It just executes some SQL. And those are special. And the reason they're special is that you don't actually have to run any compiled code to execute that stored proc. It's kind of like a prepared SQL statement, if you will, because all it has potentially is arguments and a result shape. Okay, so in this case, there are no arguments. We could add some. In fact, I will in just a moment, just to make it a little bit easier. Okay. So here's the name, and then here's what it produces. Okay, ID, T1 text, T3 text, T4 text. Okay, with the is not null. So this is the shape of the result. This is the statement, and these are the arguments in the statement. There are none. Great. Okay, so with this combination of facts, you know what the shape of the result is, and you know what SQLite you need to do to issue it. So in principle, you could say from Java code, directly run this, binding nothing, and get this shape. And this tells you, what code you might want to generate. So what this is great for is if you're trying to, say you're trying to call this procedure, and you want to call the native version and you're trying to create JNI binders or something like that. You can use the JSON to know the shape of the thing you're calling so you can auto-generate whatever binders you want. You could do the same in Objective-C, you could do it for Java, you could do it for Kotlin, whatever. Now, as it happens, we wrote code before all this JSON existed for doing binding in Objective-C and in Java. But actually, in hindsight, well, okay, hindsight, we didn't have the JSON at the time we created those binders. If we'd had the JSON, we never would have done the binders. We would have just done it with Mustache or something like that, starting from the JSON, because the JSON tells you everything you need to know. And that way you can have whatever language bindings you want with whatever calling conventions you want. And this kind of is telling you sort of what's the surface area of these procedures, okay? So there's also simple inserts. Okay, here's a simple insert, and T-insert counts as simple. Again, it was just a single store proc. Okay, there's the arguments. So this one you can see, actually we don't need to do an example with arguments because we have one right here. Okay, notice the arguments came out as though you had typed them, T1, T3, T2, T5. You don't have to worry that like was used. Okay, and it does some interesting stuff here. It inserts into T and it uses T. Actually, we didn't mention that. There was information about that up here too, is there not? Yeah, it reads from T and it uses T. Okay, so one of the other bits of information you get is stuff about the transitive closure of what the procedure used, to the extent that it's visible. So in this case, we're using just T, okay? But for instance, if inserting into T invoked a trigger, which could also insert into U, that would be listed here, right? We would say we insert into T, but we actually use T and U. So you can get a sense of what might the procedure affect and what does it potentially depend on. And that can be very useful for deciding when you might want to reissue a query, for instance, okay? So if you have some set of queries that your program uses to keep its view open, like Messenger does for threads, by looking at the query that's used to produce threads, you can determine which tables are affected, and if any of those tables change, then that tells you that you need to rerun that query because it's potentially dirty. Okay, so here is the insert. Here's the columns that we're inserting, and here's the values that we're inserting for those columns. Okay, the value is question mark, and it's bound to ID, just question mark, bound to T1, bound to T3, bound to T4, bound to T5. This could have been something like question mark plus 5, if you inserted, if there was some arithmetic or something like that. Okay, so the question mark just includes, this is the value expression, and there could be more of these. In fact, you could have done like, there could have been 2 arguments, and then you get something like this. You might have got like, I don't know, if you were adding the ID in T5, which doesn't make any sense, but okay, well, anyway, never mind. That one doesn't actually make any sense, but you get the idea. If the value has a more complicated formula, it might be using several of the arguments. Okay, so this combination of information basically lets you issue that insert statement, and this tells you which binds you have to do, okay? So wherever your ID is coming from, you bind it into position 1, you bind this into position 2, 3, 4, you get the idea. Okay, these are the most simple inserts with just a straightforward, simple insert statement with simple values. And looking at these, you can actually do more complicated things. Like if you wanted to treat this as an upsert, you could do different cogen. This tells you that the fact that it's in this insert section tells you that it's a very straightforward insert with no weirdness going on. This form general inserts could include stranger logic like insert select, insert from a select, or insert with a with clause. Those are not readily replaceable. Like you can't like look at that insert statement and say, oh, if I wanted to turn that into an upsert, I know what to do. So this actually provides the same information as these, but it's in a separate section so that you can see immediately which ones could be potentially rewritten as an insert and which ones can't be rewritten as an insert. Otherwise, there's no difference. Updates look exactly the same. We don't happen to have any. The statement would be a update set, and then there's the statement and statement args. It really looks exactly the same. There's just update statements, right? It'll have the same dependencies, so you can see what's inserted. Well, there won't be an insert tables. It'll be updated tables. And you'll see which tables are used. So the update tables in this case are like, there's only the one, right, for insert, and there's only the one for update. There's only one table you can update. Likewise, deletes, exactly the same. It's a simple delete statement, and that means it's a procedure with just one delete statement. And then here we have finally the general section, which is procs with control flow. Basically anything that's more than one statement, anything that's not a simple select statement or a simple SQL statement, one of those 4 kinds above, and including 5 if you include general inserts, goes in this section. And in these ones, you just get the signature of the procedure, not the body, so you know how to call it. This particular one had no args, so it's pretty simple. You can see it uses tselect, okay? So there's a transitive call, which can be very useful if you care about that. But the program doesn't necessarily have visibility into all the things that tselect does. So, because tselect might be in a different translation unit. So you don't always get the full transitive closure. You get the transitive closure of what's visible. And here we have basically no information on uses tables, again, because all the table usage is hidden inside this one. So you have to look at tselect to figure out what the table usage is, which you can do. So you could sort of compute your own transitive closure to the extent that it's available. And uses database means that it will require the DB argument. So if you're calling this procedure, it's going to have that database signature, like it's going to have a hidden DB argument, and it's going to return a SQLite code. And then we haven't talked much about regions. Maybe I'll do a video on those, but you can have schema regions so that you can have islands in your schema where you say, hey, this part of the schema isn't supposed to know about that part of the schema. So you can sort of prevent your schema from having wonky dependencies that don't make any sense. You can lay down formal rules like, here's the shared parts of the schema, everyone uses those, and you're supposed to use your stuff, and you're not supposed to even know he exists over there, and he's not supposed to know that she exists over there. So they're not, those unrelated schema regions don't talk to one another. Ultimately, that's what that's for. This gives a declaration of what all the regions would be. And if you have any ad hoc migration procedures, they appear here. And that's it. And there is a full grammar for this. Let me just open it up. In fact, this is a good time for me to do... let me just bring a browser onto the screen so we can see. Okay, I edited out me fumbling with full screen. I still fumble with full screen on Macs. Okay, so the formal website is up, and the docs are updated directly from the open source GitHub stuff with Docusaurus. So they're up to date. And I just wanted to point out the railroad diagram. Oh my goodness, the cursor is so small. Okay, the railroad diagram for the actual grammar is here. You can go visit that, and you can see all this kind of goodness with different statements and kind of what their shape is. Or you can see the grammar parts. The grammar is also published, and if you don't feel like reading the .y. But importantly, there's also one for the JSON. And of course, the JSON is subject to being extended in JSON kinds of ways. But I thought the diagram would actually be very useful to see. So you can see exactly what's being produced. And you should know that the grammar that's used to create this diagram is also used to validate the output of the JSON output. So we always know that the JSON we're producing is conformant to the grammar, because if the JSON becomes non-conformant, the tests fail, and the grammar has to be adjusted. So the grammar's in sync. The diagram comes from the grammar enforces the results, so you can be confident that the diagram is accurate, and plus or minus. I only update the diagrams every week or so, so you can regenerate the latest diagram if you wanted very easily. But here you can see all the different things, so here's what a table looks like. Here's all the different things that might be present. Some things are optional, some things are not optional. And then you can kind of go through each of these different guys, and there's basically a hunk of grammar for each section. Okay, the table one's fairly complicated because it also has all the column definitions, and those can be fairly complicated. All the stuff for foreign keys and whatnot. And then we can look forward to, here's what an index looks like, right? It's got names, table name, so you can see all the different fields and so forth that it has. Okay, and so this gives you a very clear sense of like what's actually going to be in the JSON and what the options are. Almost all the fields are very self-describing. And if you want more details, you can actually look at the code that generates them. It's pretty heavily commented, so you can see where they come from and what they all mean. But it's all designed to be very, very approachable. So I don't want to do too many more things, because this video is already long, and it'll get even longer. But you can see all the information about each of these guys is there, so you can get a real good sense of how it appears and whatnot. So if we go back to the code, I'm just going to do one more example here, so you can kind of see how this might change. Maybe I'll do create index I on T ID. Okay, and I'm going to change the select. So we're going to say ID integer. Great, ID integer, and then we're going to say where t.id equals ID. Okay, and actually, you see here, part of the reason why we do this, fumble fingers, this is actually valid, right? You don't have to say t.id. You can just say ID, and so by having this with the underscore, then it's always clear, what's going on there. Like that's the arg and that's the column. Okay, so let me just run that again, and over here, I have to do tprint. I have to plumb this through. So I don't know. Instead of doing anything complicated, I'm gonna just pass a constant. Okay. So let's look at x.json now. It's just it's gonna be a little different. Okay. This table now has an index I, so that's new. Let me skip to the end of this. Here's indices. Okay. There's an index I. It's on table T. And it's on columns ID, and they have for simple sort order. Okay, the query changed a little bit, so that query now has arguments. Here's ID integer, and if we look at the statement, the projection is the same, but the statement is a little different. It's got a question mark in it now. The first question mark is bound to ID underscore, and we know what ID underscore is because ID underscore was the name of one of our args. ID underscore. Okay, the integer arg, right? And then if we look here, the inserts are the same. I'm going to skip those. Update general, no change there. Okay, and notice there's no change in this because the general procedure, there's no information about the body, only its signature. And its signature didn't change because rather than add the ID argument, I hard-coded 1. Okay, which is dumb, but whatever. It's fine for this thing. And I still added no regions or ad hoc migration procs. All right, so that kind of gives you a sense of what's going on in the JSON. The JSON is great for lots of things. It's great for CodeGen, but it's also great for additional validations. Like, for instance, suppose in your system you have a strong naming convention for procedures. Great. You don't have to write a complicated parser. You could just generate the JSON for every compiland, and then scrub the JSON for names. You can have a naming convention for tables. You could enforce that underscore trailing name, trailing underscore on column names, for instance, if you wanted to. You could do whatever enforcement you wanted, using the data that's in the JSON. You can use it to compute dependencies, and to stitch things together, to figure out when things should be rerun or whatever. Basically, it gives you a convenient way to do validation and analysis on your schema. You can also do other funky things, like maybe more funky than just region support, right? You could have whatever ad hoc rules you wanted about how your schema can refer to different parts of schema. Maybe you always want to make sure you index in every table has an index, or every table has an index on its primary key, or something. Okay, whatever rules you might want, you can use the JSON to kind of examine your schema without having to do all that funky parsing, and then just look for the signatures that you want. And it's much more approachable to just, the JSON's really comparatively easy to crack, and it's comparatively stable. So whereas, trying to parse the full SQL syntax is pretty complicated. Like, how do I find all the foreign keys, and what about all the places they might be, or how do I extract the default values and so forth? You can find all those things very easily in the JSON, because they're basically put out there on a silver platter for you. So use it for creating bindings. If you want to call your sort procs from some different language, you can use JSON plus mustache or something like that to generate the wrappers that are going to call the native procs. Very straightforward to do. I'd be happy to publish some of other people's bindings. We could put them in a directory somewhere in the open source, so that others can share them. So you can use bindings, you can do validation, and yeah, great. And whatever else you can think of. And that's all we got for today. So thanks much.